I'm happy to be here today. I do want to note, I think this is my second time to talk to Technical Society of Knoxville, the first being probably literally about 20 years ago when I had just started at UT, and probably at that time talked about electric vehicles. But today we're going to talk about the grid and renewables. So let's look at least in the United States, where does our energy consumption go? And this is not just electric grid, but energy in general. You can see a large portion of it is petroleum, which is mostly going to vehicles, quite a bit of natural gas, and then coal and nuclear. And then the renewable slice is about 11% of our total energy consumption. And you can see at least a lot of that is hydroelectric, and then there's wood and biofuels. And then you can see wind is also about 20%. And then the other smaller amounts are solar and geothermal. Now, if we look at our electricity production, you can see that at least in terms of electricity, again, fossil fuels are accounting for about 63% for our electricity production. Natural gas now is more than coal. Coal has continued to go down, mostly because natural gas has just ended up being cheaper today than it is for coal. And natural gas plants are able to ramp up and down more easily than coal plants. So our coal plants are quickly being decommissioned, and not necessarily because of the environmental aspect. I think that's played a role too. You can see nuclear is about 20% of our electrical, and then renewables make up about 17%. You can see that if we look at our renewable breakdown, hydropower makes up about 7%, and wind right about 7%. So hydropower, of course, has been around many, many years, and that's what TVA was created with. Wind is fairly new, really about 20 years in terms of generating any significant electricity. And then you can see the others, including biomass and solar. But all of these, with the exception of hydropower, expected to grow quite a bit in the next few years, as we'll see in just a second. If we look at our transportation sector and our combustion of energy, you can see that a lot of that has to, right now, is still fuel oil, gasoline and diesel. There's quite a bit of natural gas used in our transportation systems. And then just a little bit of electricity here, that's in gray. And then this is projecting 30 years to the future. And you can see that they're expecting to be quite a few more electric cars, a lot more compressed and liquid natural gas, but it's not really going to displace too much our conventional resources. Perhaps it will displace some of our fuel oil, but some of the other, it's going to be about the same, mostly because our total consumption continues to go up. If we look at this from a global perspective and our energy, you can see renewables, nuclear are much less than coal and natural gas and petroleum today. But you can see that if we again project 30 years to the future, the renewables will be making up the highest percentage. It's going to go from 15% to 28%. Pointer here. But the others are going to decrease as a percentage. But even though they're decreasing as a percentage, their total amount is still increasing. So although renewables is growing at a faster rate, which is good, and it is going to end up being our highest by percentage, the others are still increasing. It's not like they're going to be decreasing anytime soon. If we look at where is our carbon dioxide production, which some people attribute to global warming, if we're trying to reduce our CO2, this is showing the different sectors of where those reductions can be made. And so part of that reduction can come about because of having higher mileage requirements on vehicles. Part of it is by producing electricity more efficiently, more efficient lighting. Part of it is by nuclear. But you see, by using renewables, it's only going to reduce our CO2 by a small percentage, about 12%. Because again, it's not displacing a whole lot of the other, but it is, so it's basically going to require consuming less electricity or producing it more efficiently, transmitting it more efficiently in order to reduce our CO2. So if we look at all of our different renewable options, I've kind of put these in two lists. On the left are the key renewables, and on the right are other. And so I certainly think solar and wind, which are probably the two that come to mind of everybody when they think about renewables, are the two key ones. Biofuels is going to, I think, play a large part. Originally, a lot of the biofuel came from crops like soybean for biodiesel or corn for ethanol. They've looked at cellulosic feedstock, but I really haven't seen that take off like some had thought with the switchgrass and whatnot. And they're now looking at other things like algae and whatnot that perhaps is more promising. Another key aspect of the renewables is storage, and I'll talk more about this. And in my mind, at least, storage is the key with renewables in terms of having a high penetration level. Some other renewables, which I think will continue to grow, are geothermal, both for heating and cooling, but also for generating electricity. And then I think some things involving the ocean, be it wave energy or tidal energy, will also, but I think these are going to be specific locations and not really benefit things as a whole. Hydropower will continue to be important, but I don't see us doing a whole lot more there than what we already have today. So if we jump into solar power, basically there's two main options. One is photovoltaics, which directly generates electricity through the photovoltaic effect, changes sunlight into electricity. And then the second one is where basically it's generating heat, different options. And then that heat is basically turning a turbine to produce electricity. PV costs have really dropped tremendously in the last few years. And so that it is very competitive now with other forms of electricity. And so I think they're basically producing as many panels as they can in every location because people are installing these very quickly, either as individuals or in larger PV arrays. And then, as I mentioned, the other option is the thermal, and there's several different types of thermal. This is showing one where perhaps light could be reflected and heat up. Concentrated on a fluid, which then that fluid could turn a steam turbine. And so this is the other option. So there's certainly pluses and minuses to solar. Solar's most widely available because it is available everywhere on Earth, just some places better than others. And it can be, small, meaning it can be rooftop. And I think another thing that we're going to see in the next several years, it's going to be more integrated into our building materials. Instead of installing solar panels on your roof, it would be much better if your roof was solar panels, literally. And then there's the thermal aspect of solar, meaning the waste heat can also be used for heating water or heating space or even cooling space and things like that. Some of the cons, of course, solar varies quite a bit. It's only available for a few hours. And so again, that's why storage is really needed to make it more attractive. It's fairly costly upfront and takes many years to pay back. And because of that fluctuation, it has a lot of stress on the grid. California, for instance, they have a large ramp up every morning in terms of how much solar they have. And it puts stress on their grid at being able to manage that ramp up and ramp down each day. So this slide just shows where large PV installations are going in. And the different darker colors is basically the quality of the solar. You can see quite a bit has gone into California. But if we look in the east, you can see there are places like New York, Massachusetts, New Jersey, and then North Carolina, where there's quite a bit going in there, but not as much necessarily adjacent like here in Tennessee. And so I think one question obviously would be, well, why does North Carolina have so much more than Tennessee? Because their solar in terms of quality really not any better than the solar quality here in Tennessee, because we're basically about the same latitude. And so it all has to do with incentives or requirements. And so this figure is showing the renewable portfolio standards throughout the United States. This is from 2012, but it really hasn't changed a whole lot since then. You can see that the Southeast, including Tennessee, essentially does not have any renewable portfolio standard or goals, whereas most of the rest of the country does, except for a few states out west. So this is showing some of these renewable portfolio standards as of last year. And some of these are fairly aggressive. You can see like California, they want to have 60% by 2030. Hawaii is going to be all renewables by 2045. Maine and New Mexico, 80%. But even these other states have, 40, 25%, 35%, fairly aggressive standards that they've put in place. New York, 70%. Texas already met their goal many years in advance. Washington State, 100%. So again, Puerto Rico. So all these states have put in these standards to kind of incentivize industry as well as make their utilities basically require to buy renewable energy. So wind power is another source. Basically, it's converting the kinetic energy in wind to electrical. It's becoming a much higher percentage of our renewable generation, both in Europe, United States, and lots of Asia as well. A lot of the wind turbines today are fairly big, typically megawatts. And the largest is about 10 megawatts for some of the offshore wind turbines. Wind is a little bit like solar in that there's some uncertainty, variability in the wind each day, but at least we do have wind at night in a lot of places. And there is, if you look over a broad area, typically some wind most all the time. However, the generation capacity is fairly low. I want to point out here, you may have a 1 megawatt wind turbine, but if we look at over a whole year, it's not going to be producing a megawatt on average. It's only going to be producing about 250 kilowatts or 350 kilowatts on average. And so you're not getting near as much out of your investment in that case. Again, some of the pros and cons. Pros, at least wind doesn't require as much footprint or area as solar and hydro. Can be built offshore. And just like solar, the fuel is free. Some of the cons are the best wind is typically far from load centers. I'll show you a slide later. I talked about intermittency. Energy storage, these megawatt, not necessarily viable today. There is some noise pollution with that rotational equipment, and it can kill birds and bats. But I will note that just buildings kill lots of birds today. Energy storage, as I mentioned, is the key, I think, for renewables. And so if somebody can come up with a cheap, reliable energy storage, it will change how our grid is operated, because we have to balance our generation and our load real time, continuously. As load goes up, you have to have that much generation. If you have energy storage, then you don't necessarily have to balance real time anymore, because you can store if you have excess generation, or then you can pull it back out of your storage when you don't have enough. And so I think that is what's going to change our grid here in the future. And so PV with energy storage, again, makes the PV much more valuable, because you can store it and use it later. You don't necessarily need to use that power at noon. You may be at work at noon, and it would be nice to store it up and use it when you get home in the evening, or charge your electric vehicle in the evening when you get home, as well as use it to provide backup power. Also can provide what we call ancillary services, which maybe helps the grid frequency or reliability, may help regulate voltage, things like that. If we're looking at what sort of batteries are being installed, at least recently, it's mostly lithium ion today. More than 80% is lithium ion. Lead acid is just very small today. So lithium ion has essentially displaced lead acid as the battery of choice. But we're still needing something cheaper. If we look at some of the things that energy storage allows us to do or helps us, it's things like improve our voltage support, could provide uninterruptible power supply. It could allow smoothing our renewables, help us to regulate frequency, and then larger things like energy arbitrage, meaning shift the time of use. And another important thing is defer transmission and distribution upgrades, meaning we don't necessarily need to build more transmission lines or generation centers. And so those things that I've listed, some of them need to occur at second level, meaning pretty fast. Others, not quite as fast, but still seconds to minutes. And then others, over longer periods of time. So this kind of, you can see that your energy storage, in some cases you need fairly high power because it's got to be very quick. Other, not necessarily high power, but maybe high energy because it's quite a bit of time involved. So this is showing some of those ratings, again, seconds, minutes, hours on the left here, and then power across the bottom. And you can see things like pumped hydro, like the Raccoon Mountain that TVA has near Chattanooga, compressed air, which would be, you could store air in a shaft, basically fill it up and increase the pressure, and then pull that air out and use it to drive a turbine. Various types of battery technology, but people are also looking at flywheels, supercapacitors, and supermagnetic energy storages. But we really still need something better than what we have today. So in terms of roadblock, the roadblock really is cost. And you can see this timeline here that cost has come down pretty rapidly. But you can see as it's coming down, that angle is changing, or that slope. And so one of the goals here you can see was about $150 by the year 2023. And this is approaching that, but we're still going to need it even cheaper than this price to really, what I call, revolutionize our grid. Biofuels, I mentioned, as another topic. Typically, ethanol and biodiesel are the two that we're most familiar with. I think everybody realizes when they fill up at a gas station, most of the time there's probably 10% of it is ethanol, which typically comes from corn today. Other countries use things like sugarcane, like in Brazil. And then biodiesel, typically coming from soybean, is mixed with diesel. But I think we're gonna need to have some advanced biofuels really to be more competitive and displace more of our existing fuel infrastructure. Still, one of the issues with biofuel, of course, is you have to grow it somewhere, and you may end up competing with food for people or food for animals. And there is some energy required to grow the crops, and you do have to be careful about pollution in terms of like fertilizer runoff and things like that. So if we continue to talk about the electric grid, one of the key standards is IEEE 1547, which is the standard for interconnection and interoperability of distributed energy resources with associated electric power systems interfaces. Quite a mouthful. This is basically a standard that's put out there, and then it's up to individual utilities whether they actually adopt it or not. But most utilities have adopted this as their interconnection requirements for people wanting to install PV in particular, but also other small distributed energy resources. But this standard has changed significantly through the years. You can see in 2003, if you had abnormal voltage or frequency, you were required to disconnect, basically turn off. So if there was a problem in the grid, they basically told you turn off, which I at the time thought was not the right way to do it. You know, I said, you know, you really need to try to help the grid out, not just disconnect. But it was small at the time, and it really didn't affect things much. You can see about a decade later, they changed it from shall disconnect to may ride through, which was basically saying, well, you don't have to disconnect, and it's okay if you hang in there. And then you can see just a few years later, they went from may ride through to shall ride through. So as this renewable percentage got to be higher and higher, they found, well, we can't just tell them to disconnect. It's going to make things worse. They're going to have to hang in there and help things out. And so you can see essentially a flip-flop over this 15-year time period from, oh, just turn off and go away, to you need to hang in there and help us out. And so this is showing at least a chart of some of that ride through, where at least you have to be able to ride through for 1 second with no power at all, or no voltage. And then you have to ride through longer periods of time, like 50 seconds, even with pretty low voltage. And you have to be able to operate from 0.88 to about 1.1 voltage continuously. And so these are some requirements that are built into the inverters today, so that they're able to continuously operate and ride through. If we then look at some of our wind and solar resources, you can see that in this top left figure, you know, most of our population is in the east and some along the west coast, whereas our best wind resource is here in the Great Plains area. There's not that many people living there. So we're going to need a way to get more wind installed in this area where not a whole lot of people live, but we're going to have to transmit it to where people are living. Solar is not quite the same same way, because solar, essentially you can do it anywhere. But the best solar, again, is here in the Southwest, where there's not quite as many people again. And so CURENT, which I'm going to tell you a little bit about, is a research center at the University of Tennessee. Our concept is looking at these things from a wide area. How can we get wind and solar and offshore wind and transmit that over long distances so that we can accommodate a high penetration level? Right now, renewable is about 10%, maybe approaching 20% if you count hydro. But how do you accommodate 50% renewables or 80% renewables, like some of those states that we saw? Engineering Research Center focused on the grid. It was started in 2011, so we've had it for 9 years now. We partner with RPI and Northeastern and Tuskegee. We've got about 25 faculty across these 4 universities and more than 100 students. UT is the lead institution, so we've got 10 faculty in power system, power electronics, and we've got about 80 graduate students doing research in this area. So we are by far one of the largest universities in the United States that's doing research on the grid. I say we compete with anybody, even the big boys, so to speak, on power and grid research. We have about 35 industry government members who actually pay an annual membership fee to be members of CURENT, and I'll talk a little bit more about that in just a second too. So this shows our CURENT and industry members. Utilities include TVA, Dominion, and things like KUB and Electric Power Board in Chattanooga, but it's also got New York Power Authority, New York ISO New England, Southern Company, which covers Georgia and Alabama, General Electric, Raytheon, Eaton of the world. And then I'm proud to say we've got 5 national laboratories that are members, including Oak Ridge, of course, but also Pacific Northwest, Sandia, Lawrence, Livermore, and National Renewable Energy Lab, as well as locally EPRI, the National Rural Electrification Co-op, and then GARENA, which is an arm of basically China and their research. We have some nice facilities at the university. We have a nice visualization and control lab, some high power labs to look at the grid, and a grid emulation lab that we'll spend quite a bit of time talking about for the remainder of this presentation. Being a university, of course, we are concerned with education, of course. And so CURENT is charged with doing things even at the elementary and middle school level, organizing things like science fair and parents' night and lab tours. We work with high school students and we provide research experience for teachers, try to help them develop teaching modules that they can take back to their school. Again, this is to try to encourage more kids to go into electrical engineering and power, or just engineering and science in general. We consider that to be a win, of course. This slide shows one of the things unique to the University of Tennessee is we have a bunch of monitors called FNet throughout the US where we can monitor the frequency. And all of that data is sent back to UT. And so when an event happens, we can see that event occur and kind of visualize. This is going to show an outage of a large generator in Florida, but it's going to basically impact the entire eastern United States. And you can see that frequency impact as it jumps around and oscillates basically even impacting Minnesota and Maine from an event that happened in Florida. And so we're able to see things like when earthquakes have tripped nuclear stations, and basically send text messages or emails to the different utilities who are members to say, hey, an event occurred in this location. Because utilities, they know what happened within their own grid, but they don't know what happens in their neighbor. And so by having this, they're able to kind of know what happened and where it happened. We hope that in the future, this tool will help us to take some proactive action to mitigate so that we don't see those oscillations occur long distances, but be able to maybe damp those locally. We've also built what's called a hardware test bed to emulate the electric grid. And basically we are looking at the entire US. And today the US grid is divided into three. It's got the Eastern Interconnect, the Western Electrical Connection, and then Texas, ERCOT. And Texas has always been kind of independent, so they have their own grid. These three are very loosely tied together. Very little power is actually transferred among them. We're saying in the future, it might make sense to add a high voltage DC, this light blue line, where you could transfer large amounts of power from the east to the west or vice versa. And you could imagine as the sun moves across the US, maybe in the morning, some power could be transferred one direction, and then later in the evening, transferred the other direction, just depending how much solar and things like that. Could also be used for wind as well. We have a very nice visualization wall that looks kind of like what a control center would look like. And so we are able to do some nice things with that. We also look at microgrids. We have a project with the utility in Chattanooga. They're installing a microgrid that's got, as you can see on the bottom, this PV and a battery, and we developed a controller to help manage how many loads they can serve. So they can serve an important load, meaning the airport very close by, but then they can serve more load if they have enough energy storage or PV. And so this has helped us develop a controller and test it out in hardware before they go try it out on their system. This is showing how with more PV and we're able to expand and do a larger area. And then we've also done things like look at faults and be able to detect a fault and isolate a fault. So it's been a very good tool for us. We also do a lot of research in power electronics. We've looked at things like smart homes. We've looked at doing things for the next generation or next generation of airplanes. Quite a bit of utility, which I talked about today, and renewables. We've looked at data center power supplies, make those more efficient, and medical devices. But we're going to focus again on renewables and utility applications. We've got another test bed called a large-scale test bed. And basically, it's a simulation tool. It's able to use a lot of commercial software tools as well as some tools developed by the University of Tennessee. And we're able to look at things and visualize things on a screen here. And this tool has also been set up and shared via the web so that other people who can use this tool and be able to do some things. And so we have some fairly unique models where we're looking at fairly high levels of wind and solar penetration in these large grids and try to learn how can we control things. Our hardware test bed, we're able to look at things like offshore wind. This is showing a fairly large offshore wind here in the Northeast off of Massachusetts, Connecticut area, and then using HVDC to connect that onshore. And so basically we're able to build this circuit in hardware. but we use power electronics to model our generators and loads. And this has some advantages that I'll talk about here in just a second. Basically, our power just circulates. From our DC bus, we use an inverter to produce an AC waveform. And then we have a load, which is basically a rectifier, which pulls power in. Storage, of course, has to be able to accommodate power in or out. So our AC grid here that we're emulating basically has generation, load, and storage, much like the grid of today. But instead, we don't have these large mechanical or chemical batteries and things. We just have power electronics. And we have to make up the power losses is about all that we have to do. This is actually a fairly complex, meaning the grid has all of these things that have to work interoperably. Things locally have to run, like maximum power point tracking and your loads, they have things that are running. Then we have things running at a larger regional level, where you're looking at the state and doing some estimates. You're forecasting load. You're forecasting how much wind and solar you might have. And then you're actually even, some of these regional levels have to work with other regions and maybe share or buy power. So our electric grid of today is a very complex tool that's developed over 100 years. And so we have to be able to have all of these same things running in the tools that we develop. So right now we've got about 15 cabinets, and we're able to look at things like 80% renewables, and we're able to fully monitor and test many different things with our test bed. Like I mentioned, we have a pretty nice visualization room that we're able to look at things. Some of the advantages of having this test bed is we can do things from microseconds to milliseconds to minutes, which actually, and it runs in real time. So there are things like simulation tools. Most simulation tools do not run in real time. And so that's one of our advantages. We do have communication, protection, and increasingly we're trying to look at things like cybersecurity. And so this has been a bridge. I call it, it's somewhere in between a simulation and the real grid. Some of the disadvantages, of course, is it did take many years to build this, and it takes quite a bit of space to build this hardware. We have lots of tools in our emulators. We have synchronous generator, we have motors, we have wind, solar, we have transmission lines, we have faults. We can actually put a fault on the system and see what happens. So I'm going to run through these pretty quick, and then we'll wrap up things here in just a few minutes. Our synchronous generator emulator, I don't want to delve into the equations and whatnot, but I did want to just show it does have electrical, mechanical, and our excitation model. All of these are built in. And so if you look at these terminals here, which is basically looking at the voltage and current, you would not know that it's just some power electronics. You literally would think this was a synchronous generator in terms of how it behaved, because we have modeled it to behave like a synchronous generator behaves. Same thing with a wind turbine. We've modeled it to behave like a real wind turbine would, meaning when you have more wind, the wind speed increases, you're going to have higher current level. Or the wind decreases, lower speed, you're going to have less power, less current. Same with solar. If you have high amounts of solar, you're going to have higher amounts of current. And then if your solar irradiance changes, your current will go down. So again, we're able to model all of these things in our emulators. Same thing with battery. We've looked at lithium ion, we've looked at flow batteries and made them look just like a battery would on the grid. Transmission line. The main thing we want to model a transmission line is to look at things like, what if you lose a line, means something opens, or if you have a fault, we can actually model and make it look like a fault and it occur at different points on the line. Or if you have parallel lines and maybe you have a fault, well, you don't lose all your lines, you might just lose part of your lines. And basically you're just changing the impedance here, but we're using power electronics to do that. This is showing a scenario where we're transferring power over a long distance. And as we increase the load, eventually we're not able to do that because we're not able to regulate the voltage well, and you hit what's called a collapse point. And in CURENT, we developed a tool to predict where that occurs, meaning where our stability margin goes to zero. And the reason we did that is, well, you want to avoid that, of course. And so you can avoid it by, when you get close, you inject some reactive power here to help regulate the voltage. And you can continue to increase the power that you're sending from one end to the other. And you're able to maintain a safe margin so that you can keep a stable grid. We developed a structure to also represent the western part of the United States. We call it our 4-area system. But with high penetration levels of PV, wind. So it's based on the grid of today, but replace some of our sources that are currently coal and natural gas and replace those with PV and wind, and look at how can we control things. And look at things, again, the grid is easy to do when everything's running and fine. But it doesn't work well when you lose a large transmission line or large generator. This is showing what happens when you have a large line trip, for instance, between 2 and 8, sending power down to California. And by using our control method, we're able to bring that back, our frequency. You can see we're able to bring it back to about 60 hertz. With no control, the purple, you can see it just oscillates and you end up losing stability. So that's just what I wanted to touch on today. I hope I was able to give you an idea about some of the issues surrounding renewables and things that we're going to have to address as we get higher penetration levels, and then also introduce you just briefly to CURENT and a little bit of the research that we're doing here at the University of Tennessee. So I'll be happy to answer your questions.
All right, I've got a 2-part question, and then I will unmute everybody. But another way you can ask a question is use the chat feature. You can write your question down, and Dr. Tolbert can see it and answer it. My question has to do with transmission of energy across the country. One question is, how fast? If California needs a burst of energy from the East Coast, how fast can that energy get there? And then the other part of it is, where are we now on superconductivity transmission lines? When will we get that? Or is that like fusion power in 20 years in the future?
So the first question about sending power transcontinental or across the U.S., it's done in less than a second. It can't be done today because there are no transmission lines of substantial size that could carry that power. So that would be the issue. We would have to build these large lines, and nobody is going to want lines built through their state if they said, oh, this is to send power from New York to California. Well, Missouri's going to say, I don't think so. And so I think we're going to have ways of of tapping that power at multiple locations. And so we have looked at things called multi-terminal HVDC, where you can tap that power off at different places. And then the second question was about superconductivity. I know Oak Ridge National Lab did a lot of superconducting research on cables and other things and made a lot of gains. And then DOE kind of abruptly in the early 2000s ended that program. And so there have been a few demonstrations, but I think it's really more of a cost issue than it is a technology issue today. Of course, some would say that goes hand in hand, that you need technology to develop a cheaper way of doing it. But they've demonstrated the ability to do that, where they basically can have, sorry, my youngest is here. Go ahead. So yeah, one of those benefits of working from home. So with superconductivity, I do think it's a niche application. You may see it used in some places like New York City, where you just don't have the space to put more power lines underground or here or there. And it would be nice if they would do that other places, though, where they could run it underground. I do think part of the issue is being able to maintain cryogenic temperatures and some of the losses associated with that, the cost to operate it. But from a technology standpoint, they can do it, but I think it's just much, much more expensive than what they have today for overhead lines.
Well, I've unmuted everybody. A few people still have themselves muted. You'll have to unmute yourself if you want to ask. We have one chat question from Wolf.
And I'm going to have to stop share. So
what are the key differences in the behavior of long distance DC versus AC transmission lines?
Very good question. So with AC transmission lines, the main issue is the stability. As you get basically longer than 500 miles, you can run into some stability issues, being able to send power over such a large distance. And that's where DC would then become favorable compared to AC. DC, of course, requires 2 lines. AC is 3-phase, it's usually 3. So from a conductor cost, DC is cheaper. But because it has to interface with AC on each end, you have to have power electronics on each end. And so those power electronic stations are very expensive. So typically DC is only cost competitive if it's longer than 500 miles. So in some places like China, they have lots of high voltage DC, for instance, from the large dams that they've built out in the west to bring power to the east. The US, we have a DC in the west that takes power from Washington State down to California, but we don't have many DC lines. The nice thing is with DC, you don't have to synchronize things like you do with AC. And so it's a little easier to put power on and take power off. You just kind of have to manage the voltage. You don't also have to manage frequency. So I think we are going to see more DC lines in the future, both at high voltage. I think we're going to see more DC at lower voltage. Why? Because our PV is DC, our batteries are DC, all of these things we plug in the wall are DC. You know, they're having to change AC to DC. So I think we're going to see a slow shift to DC.
Can I ask a question? I
Go ahead,
read
Bruce.
recently of coax cable that was 3-phase and nitrogen cooled. that was supposed to be a superconductor type of cable. Are you familiar with that?
Not that particular one, but that's, again, I think probably goes back similar to that superconducting question.
Yeah.
That they were able to use liquid nitrogen, sounds like, as their coolant, and run that, as you said, in the coax, and then the 3 conductors, as opposed to having 3. But that's probably, yeah, back to that superconducting question. But again, I just think it ultimately a cost issue. I do think, at least I would like to see us put more things underground as opposed to overhead, because nobody wants power lines running across them. But the trouble, of course, is the cost. Putting things underground is just so much more costly, mainly because of the cable cost as well as the trench cost. But I think we will see more of that.
Well,
Probably
storm,
because,
right?
oh yeah, they're more resilient too. Meaning, yeah, you're not going to have the ice issues or the hurricane issues or the tornado issues. So yes, they are more resilient.
Back when they were talking about the superconducting lines, they were proposing to put them along interstates. Therefore, you didn't have the land condemnation or right-of-way type issues. And it sounds like if you put 1 or 2 from one coast to the other, and then a couple interconnections, you would reduce your line losses considerably. But if we're not putting money into it, we'll never find out.
No, but I'm going to bring up a related point to what you just said, and probably something I didn't really talk about much today, is the electrification of transportation. And we're talking about charging our cars, of course, at home, or charging them when you stop at the mall or UT. But what if we electrify our roads and you're able to charge while you're driving? And so Oak Ridge and others are working on being able to wirelessly charge and be able to what they call charge in motion. And if we could electrify our roadway, then you don't need as large of a battery. You don't worry about, I'm going to run out of fuel, meaning run out of charge. I can charge a little bit as I go along. And so I do think being able to have high power conduits along our roadways, I can imagine that coming, both for getting power over long distance, but also just to be able to power our streets.
Yeah, I got a follow up on cost. Is given that utilities are already under financial strain, like both TVA, Pacific Power, and the rest, and as more people go to their own photovoltaics, and the revenue for the utilities is lessening, where's the money going to come from for paying for big projects like long distance transmission? Or, it's the same problem with nuclear. It may make sense at a top level, but the utilities don't have the money to pay for it.
Right. And so I think there's this push and pull between, is it going to occur at a large centralized level, sending things over a great distance, or are we just going to have lots of small put in people's houses? My guess is, at least initially, it's going to be the latter, meaning it's going to be the small things that are done at houses. TVA is already starting to change how do they charge, and not just charge for kilowatt hours, but just charge for, I call, connection fee, because people are already doing some of this. And certainly being able to connect to a grid and use the grid as your storage, meaning sell power back to the grid or pull it out of the grid, that's a whole lot cheaper than batteries. And so having a grid certainly means you need less batteries and makes it much more cost effective. I don't know where the money will come for a large project. Like you said, there's very little appetite for something like this now. It would require quite a bit of government incentive to do something.
That's a point that I'd like to bring up is when we had our old road system before the highway system, it took a national effort to develop our highway system. And do you forecast that power transmission use and delivery will be a federal issue, especially since the idea of electric transportation on our roadways and railroads? What's your thought?
Yeah, I do think it will be because I think society as a whole is just becoming more and more dependent on electricity and power. You know, it's every time the power goes out for a few hours, you know, you just realize, holy cow, I can't do this, I can't do that, you know, and young people can't get on their phone, can't do internet, can't do this or that. So I think because it is so important to society, I do think there'll be increasing federal involvement in the grid. I do, you know, there have a lot of efforts on cybersecurity already and other areas as well.
My other question is regarding these large transformers and transformers that require either replacing them, which takes about 3 years to build. Is there any thrust in the size or maximize the size of these distribution transformers to protect us from having a massive failure?
So I don't think necessarily along the lines of what you're implying, Steve, in terms of reducing sizes and maybe putting some in parallel so that, as you indicated, you lose one of these large multi-megawatt transformers, it's more than a year to replace it. What they have done is look at things like develop a portable transformer, basically just a tractor trailer that's got the transformer built in where they can move it to a site that's needed. They've also looked at a power electronic converter based transformer. And then they already have agreements among the utilities to share their spare transformer stock. If somebody loses one, to buy one from a neighbor or share one from a neighbor. But I think that is an issue they're well aware of. I think they're still working on it, though. I do want to
what would be the potential of running transmission cables through hyperloop tunnels?
Transmission cables through hyperloop tunnels. Now that's one I have not thought about yet. But obviously with Elon Musk, maybe I should be. So I don't know exactly the power requirements for those and whatnot. That's just something I haven't looked into yet. So I'll give you I don't know. I'm gonna answer a question that was posted to the chat here from Hong Yu Zhou. He was questioning about microgrids and what role could they play during like a community hazard. And I think that is one reason why some places are looking at microgrids, because as we've seen, when we have a tornado or hurricane go through some areas, it can be many days and sometimes weeks to kind of get the grid built back because of the loss of all these transmission lines and poles and towers and whatnot. A microgrid could conceivably provide power more quickly and be more resilient. But again, depending over what area it's serving. If it's still serving a fairly large area, then you may still have loss of poles and whatnot in that area. But they do think, and we've looked at some studies to show that it will increase the resilience and you will be able to get power back more quickly with microgrids.
I have a question. Given that, as you said, lithium-ion batteries are becoming more and more prevalent, and both for transportation and for stabilization of the grid, do you see any issues with shortage of raw materials like lithium or cobalt?
I don't think there will be necessarily a shortage of those materials. However, there are going to have to be better efforts at recycling the materials that are going into the batteries today. And I think there's going to need to be better reuse of batteries. We've had a couple of projects looking at taking batteries out of cars when they've kind of, okay, we've had an issue with a cell or two, maybe it's time to replace the pack, but take it out of a car, but reuse it on the grid. Because on the grid, it's not like, you know, you're stopped in the middle of nowhere if you end up with your batteries not working as well. And so we're looking at what's called second use and using the battery, take it out of a car and then use it on the grid. But I do think there are some raw materials that are in shorter supply related to electric machines, some of our permanent magnet materials. I know a lot of materials are found in just a few countries. And so I think the question there is, you know, those countries kind of dominate and hold it and can sort of even hold the materials hostage in trade negotiations and things like that.
I'd like to come back to your presentation in the beginning where you talked about projections for 2050 and how that would relate to the IPCC's report on 1.5 degree, and that we need to actually turn down the CO2 curves very drastically within 5 years, or at least 10 years, into which we have already passed.
Right. Yeah, I guess I'm fairly pessimistic in terms of we can do a lot, but our energy demand is so much that we could literally switch things over as fast as possible to renewables, but it's not going to be fast enough because we're already consuming a huge amount of power, and just the energy density of gasoline and coal really can't be matched. And so it's, you know, they're making as many solar cells as they can and building wind turbines pretty quickly. But just our developing world, meaning Asia, Africa, South America, their low consumption, you know, they're wanting to be more like US, meaning they want air conditioning, they want refrigerators, they want more of this and that, in which they should have, of course. And so that load is just increasing quite a bit. And so I think it's going to be tough. I think, but that's also opportunity, because some of these areas where they don't already have coal and natural gas, you know, if we could find ways to go in and help them with renewables to start with, more efficient use of power to start with, maybe that's a key. the main key is just reduce the amount we're using. Reduce the amount we're using.
Do you think that with a prevalence?
I cannot get on. Okay, here I am. I just wonder, with all this energy demand, how can we refuse to consider the nuclear option?
Well, that was sort of my question also. I was saying, with the coming of all electric vehicles, we will need more electricity. So concurrent with what Walter's saying, the nuclear option might be a very good backup. Don't you think so?
Yes. Oh no, I'm pro-nuclear. I'm not anti-nuclear. So we need that base generation, which is today nuclear and coal, and coal needs to go away, and it is, and I do think we need more nuclear. My concern with nuclear, of course, is what do you do with the spent fuel rods?
Well, that's a problem.
And they've put billions of dollars into Nevada, and Nevada accepted billions of dollars for many years, and then when it came time to actually put the rods, they kind of said, well, I don't think so, we're not really interested. But I think we're going to have more nuclear. So I think nuclear combined with renewables will go a long way.
Yeah. Back in the 50s, the United States made the decision, and the rest of the world apparently too, not to recycle rods, and so therefore we've been moving further and further away from that. But if you're talking about billions of dollars that go into research, I would think that we could solve the nuclear waste problem by throwing some of that money into that. And then the other thing is hydrogen fuel cells. If you have a base load from nuclear plants, you can put that into producing hydrogen fuel. Once you get where you can store it safely in large quantities, and then that would be the hydrogen fuel will basically be like a battery. You can produce more of it when you got excess power, and then use it in the fuel cells for cars and even stationary applications.
Right. Yeah. Fuel cells, I think with hydrogen, certainly nuclear at night, when we don't need that power, is a good time to produce hydrogen, and then solar in the middle of the day, wind. If there's ever excess power, it would be great to go on and do something with that instead of say, well, we got to turn it off or not use it. But of course, making hydrogen takes quite a bit of energy. It's energy intensive to separate that bond that hydrogen has with either water or whatever it's combined with. But I do think hydrogen will be a fuel of the future to some degree as well. I think, again, DOE has spent a lot of money looking at fuel cells, and then seems to they still are today, but they seem to have gotten away from that to some degree. Although they're looking at natural gas. You can get hydrogen out of natural gas, certainly, to power fuel cells. But yeah, I have a feeling we'll be revisiting fuel cells again soon.
Primary problem with nuclear is really in economics and the timeline, that it just can't come on fast enough.
Right. Yeah. Yeah. You can't afford a 20-year timeline to build these, because that means we need to be building several today.
But are there enough existing nuclear plants to renew them instead of building new one? I think the biggest problem is new new nuclear plants because people don't want them. Those that are existing, they've shown that they are not that dangerous for one thing, and it would be a good plant to extend their life rather than plan to retire them.
Yes, I wholeheartedly agree, Jean-Pierre. That's exactly what they need to do. I'm not sure, those costs involved in extending a lifetime or completely redoing them, but that's what they need to do because, like you said, it's already there. People are used to living near it. They're not necessarily going to object to, well, it's going to continue to be a nuclear plant. Anytime you would propose a new one, of course, you'll get huge objections, and it's probably just not.
And long delays in the construction. We cannot avoid that.
Right.
So
but they were not built as a modular unit, and so they are extremely difficult to take apart. And because they're highly radioactive, it's almost impossible to do that in any reasonable timeline.
Yeah. But all that shows that we need to have integrated research development for all this energy. We cannot say, I'm going to work only on the fuel cell, only on the hydrogen, only on the nuclear, only on the wind. It needs to be, somebody needs to coordinate all that to have a global view of it.
I couldn't say that better, Jean-Pierre. Yes, we have to work on all of these because it's going to take all of these to get us out of the global warming hole that we're in, and just to kind of meet the needs of society as we go forward. It really will require everything. There is no single thing that's going to do it. It's going to take all of it together. Yes.